All right, so that should be good enough, at least for the sketch, right? And also for you to process all the information. So now let's do this as a whole class as if it's a real FRQ. So the ship leaves the port. So let's say the port is at the origin, right? It'll be moving in that direction with a bearing of north 33° west. So the way you read the bearing is to find the reference direction, right? The one you're going to start with. So it's either going to be north or south. In this case, we're going to go along this direction, right? It started from the north, right? Goes to the west, right? By turning through a 33°. All right, you know what? Let me. This angle here is 33°. So the ship as it being at point A, and the distance from O to A is 24 miles. Then the ship turns, right, 90° in order to travel in the direction with a bearing of south, 57° north, west. So that was a little bit trickier than yesterday, right? So the textbook problem told us either clockwise or potentially could be counterclockwise, right? When the ship turns. But in this case, it didn't tell us. What do you think? Did the ship turn clockwise or counterclockwise? So that it will be moving in that direction, right? Can you imagine what that direction looks like? South, 57 east. So the west is now. Let's say we have a dashed line, right, which is perpendicular to the direction OA. That means the ship will be either facing this way after turning 90°, right, or the other way around. But whichever way depends on whether this direction, south 57° west, will make sense. South means that the ship will be facing south, but turn 57° to the west. So would you say that the ship must be going this way, right? That's the only plausible direction. All right. So now, oops. All right, so we're moving along that direction, ends up being at point B, up to traveling another 5 miles, right? And then you can connect OB, right, to get a right triangle, right? Now, if you seriously want to label the angle 57, the way you do it is, so imagine that if you're on a ship, right, you're facing south, right? Now, what we typically do in science, especially in physics, to let people know, or especially our reader, in what direction we're looking at, we draw a little eye, right? Or maybe some eyelashes, right? So you know it's eye, not a light bulb. So we're facing south, right, on the ship, and we are turning to the west, which is on our right, right? Turn to the west by 57°. So it will be an angle between this vertical line, which is straight to the south, right, and the side AB. So that's 57°. Okay. So it's getting a bit messy, right? In this case, let me redraw the triangle. That's a good question, right? And it turns out that I hope that if you been trying to solve this problem, and you may find that 57 is kind of useless. But they provide you to confuse you. I don't know if it was designed like that. Maybe it is. So you guys have to be, be careful with that. Anyway, so we're looking at the triangle ABO, right? And what we're looking for is the bearing of the ship away from the origin to the direction OB, right? And the bearing of it depends on the reference direction north, right? Since OB is relatively closer to the north, right, than it is to the south. But you want to find the angle between the north all the way to the OB. And that angle depends on that 33 degree, right? And the angle AOB. So now we're down to finding the angle AOB. All right, so I'm sure that you guys is now pretty good at this, right? So can anyone tell me how would you find out the angle AOB using a trig or inverse trig function? And don't forget that AB is 5, right? And AO is 24, right? I'm looking for the angle AOB, right? Oh, yeah, go ahead, Max. 5 divided by 24. There you go. Right. That's great, right? So tangent, SOHCAHTOA, right? Opposite of adjacent. Then you feed the ratio opposite to the adjacent to the sine to the inverse tan to get the angle, which works out as approximately 11.8 degree. So now the bearing angle is the sum of 33 degree and 11.8 degree, right? So you're going to say the bearing, is starting from the north, right? The angle is 44.8, right? 11.8 plus 33, west. Yes, you want. No, because you see that in this case, we didn't even find out hypotenuse, right? And remember that your goal is to find an angle, right? And it could come from the inverse tan, inverse cosine, inverse sine, because it depends on what you have, right? So if you know 3 sides, whatever you want to do. If you only know 2 sides, it depends on what sides you have, right? Oh, Alani, you have a question? Mm-hmm. Mm-hmm. Yeah. Why does it still end up being here?
Southwest.
It's definitely heading to that direction. Now, the reason why the ship is still in a northwest quadrant is that it didn't travel that much. So relative to whoever's is that the origin sees the ship in that direction. So now, right? So let's say if the ship travels, let me zoom out. Right? Yeah, if it travel all the way here, right? Then you see that, the ship is actually going all the way into the lower portion. So that's why. Exactly. Yeah. Right. So figure out how much that distance is needed to be able to cross that, the east-west line. Then that's the minimum distance has to travel to be somewhere over there, right? Well, that's something you could calculate, but it's not needed. In this case, that now this is I see that some of our students, or even all of you guys tend to overcomplicate certain questions in SAT. You didn't realize, because trust me that I think that out of the 20 something questions, there are more than you can think. the questions are designed to be algebraically or mathematically easy to do, right? But they put a lot of things to cover it to make you feel like that you have to do this and that or some complicated things, right? Now, there's another thing of this problem that makes it a bit trickier. Have you thought about why they're telling us the angle 57 degrees? We didn't even use it, right? And I think that, oh yeah, go ahead, Max.
Because, or maybe to like mislead people.
As a distraction, right? Or you feel like that. It turns out that a lot of the students realize, oh, you know what, forever, you know, whatever number they provide us, you have to use them all, right? But it might be true in math, most likely, but in science or those kind of real world situations, so those information might be redundant, misleading, right? Or, you know, they're irrelevant, right? For example, like, you know, later on, you will see that when you do some experiment, you know, let's say in chemistry, you guys have to study some chemical property of certain substance, right? So they say, hey, you know, could it be the temperature of the room, or could it be, you know, the catalyst you put in a solution, right? Could it be something else that you think that's going to affect the speed of reaction? But one of those options is, you know, the size of the beaker. Will it matter? The shape of the beaker, the container, right? The brand of the Bunsen burner, right? I mean, you could mention that, yeah, I'm using the fancy, you know, tools, right? But that's irrelevant. But when they disguise those information as a mathematical measurement, then you thought that they might be relevant. Anyway, but guys, I seriously have to alert you guys, if it's in the test, you know that once you get to this diagram, there's almost no way for you guys to miss the rest, right? And that's why, you know, I might even award you for a point or two for just a sketch, right? So now, of course, you know, I'll be quickly see that, oh, if you get the right answer, I'll go back and see if you do have the relevant work. Most likely you do, right? So you get the full credits, but nothing that only give me the final answer, because for your response, if you do get an answer without any work, then you put me in an awkward situation, right? I do want to give you points, but I cannot do that because FRQ does have to require some work, right? But if you do mess up the final answer, that's a point off, provided that you did all the rest, you know, not necessarily perfectly, but everything reasonable. Or if somehow I saw from a sketch, then some student labeled the size you know, incorrectly. So the student put 24 as AB and 5 for the you know, AO, right? And carried over, right? Of course, you get the wrong answer, right? So I think that in some of the standard tests, like the AP test, they do have something called like carried over mistake, right? They will go through your logic and see that if you were to get the right thing to start with, that you could have got the right answer, but you didn't. That's why you messed the whole thing. You get a point or two off, not that many points that you think, right? And that's why, you know, I like the FRQ, since, you know, it does get us, you know, more freedom to grade your work. So take advantage of that. Anyway, so now let me move on to the last part of a 5.8, which is something called simple harmonic motion. What's up? Yeah, just take a look, you know, and see how satisfying it is. It's what? No.
Yeah, like I started that homework. I was like, what the heck is this?
Well, but turns out that you know, in our life, it's full of those interesting motion. Wherever you see them, it's everywhere. There's even theories about understanding the whole universe using strings and vibrations. So I don't know if you heard of string theory. It's a theory that's been there for decades. Try to come up with a new way to understand the universe, to rebuild a whole system of physics. But so far, they haven't done too much, you know, but it's a beautiful theory. So pure math, you might heard of higher dimensions, like 11 dimensions. We live in a 3-dimension, right? Space plus the 1-dimension time. But string theorists think that they need higher dimension to make the math works out. It was beautiful, consistent, right, coherent. But somehow they couldn't have, the prediction of what could be measured to prove their theory is correct. Anyway, so now the reason why I'm showing you one of the slides from my old, PowerPoint for the physics class is that when you see the term simple harmonic motion, I'm not going to get into the detail of what that motion is, but I do have to let you see what it's like so that you have an idea, what they might ask you in the problem. So first off, you see that it's a motion, right? And you do see a lot of movement, right? So those are like little bead or marble that's attached to a spring, and you can, stretch or compress it, right? And let go, it's going to go up and down. So the motion of those marbles, every single one, is going through something we call simple harmonic motion. It is simple since we see that instead of only studying motion on a straight line, moving straight ahead with the same speed the whole time, it's boring, right? So we see that things are moving around, right? Changing speed. And also it's very predictable. You see that? Even though it's kind of hard to predict because it doesn't have a steady speed, but it's very predictable. And also what's good is it's periodic. So it'll never like a leaf, right? It will always go up and down around the same position, right? It will stay there. But it's harmonic for many reasons. So if you guys know, or anyone here played any musical instrument, guitar, piano, clarinet, what do you play? Piano, okay. So if you open, what do they call it? The chamber or whatever, right? They have hammer, right? The hammer is going to strike some strings. It's hard to see because, they're hidden inside, right? But, if you have those professional come to your house to tune the piano, what they do is they will tighten or loosen up, or you most likely tighten it, right? To make sure that the sound's going to be right. But piano is kind of hard to see what's inside because it has such a, complicated design, right? But very, brilliant design, right, of engineering. So now the best way to see those kind of motion and related to the music is guitar or ukulele, right? So it's very easy to see how the strings vibrate. So next time we get a chance, whoever's playing guitar, take a close look at the strings. When they plunk the string, right, you hear the sound, but now you're going to see that the string is going to vibrate and shows you this kind of motion. But it's hard to see if you don't look close. But also what you can do is use the high-speed camera of your smartphone, right? Videotape a few seconds of a clip of the guitar string vibrating and replay it. You'll see that very interesting, smooth kind of motion. And also, different strings produce at different note, right? Different frequency. So when the person plunked at different strings, you can videotape different strings. So you see that the pattern looks similar, but they have different sizes. All those, loops are, different, and the speeds are different. So now the thing is, and it turns out that for those strings, well, for guitar, I think that it's easy enough for people to tune the guitar themselves, right? They have the tuning fork, or they have some kind of a maybe fancy tool. You know that they have those knobs you can turn to tighten or loosen up the string, right? And by tightening the string to make it stretch, a lot of force in the string, it's gonna let the wave go even faster, and it's gonna vibrate even faster, and it's gonna produce a higher note. That's why, when you see that, well, that's not a C, like a note C, right? You're gonna tune it to make sure that it does produce the right sound. It actually works out just like, our vocal cord. If you, when you speak, touch the throat, right, you can hear the vibration, right? So now think about this. If you try to sing at a higher pitch, how would you do that? So can imagine that you have to put a lot of force, right, to really stretch the vocal cord to, and that's why, you get tired, right, when you do that. But when you just relax and just speak in a low voice, right, it's not going to put in a lot of force on it. This is like the guitar string, right? You stretch it, make it tighten. Vocal cords are very flexible, tissue, right? You stretch it, when you vibrate, it's going to put, a higher frequency, right? Anyway, so now you know that this is wave, right? That's the, whole entire shape and how the shape changes, right? But if you're looking at every single object, they're moving periodically in a very predictable way, right? Always going around about a fixed point, right? And the wave kind of a behavior is described by the simple harmonic motion. And you see now the harmonic motion gets the name from maybe the musical theory, right? Harmonics, it's just a combination of certain notes, right? Anyway, now there are lots to talk about, about harmonic motion. And I was telling the first two classes that if you ever have to take the physics in the upcoming semesters, I think that this will be one of the worst chapter. Yeah, well, you know what, might not be the case since, you get the math part of it. Yeah, but the hard part for people who are good at math and still get into those troubles in science classes is they need to find a correspondence between the math and the science. Anyway, so let's take a look at a typical question asking you about the things that you probably already know, but you didn't realize that you've learned it already because they have those fancy terms, right? Not to mention that they might write the functions, right, for cosine and sine in a way that you didn't want. Now, they say there's an object moves in a simple harmonic motion. You can imagine that that marble goes up and down, right? That's the object they're talking about. The D measures the distance in centimeters between the ball, between the marble, and that fixed point. So now if you want, I can show you quickly, and I'll come back in a second. So the distance, so let me have, let's say if I put a pin right here, which marks about like the center position of all those marbles, right? See that sometimes the marble might be above this pin or lower than the pin, right? So if you can measure at real time the distance between the marble and a pin, if it's above, you get a positive distance. If it's below, you get a negative distance. So that's what that D stands for, okay? Now, let's go back. All right, so D follows a function of cosine, right? So 12, as you know, is the amplitude of the function of the cosine. You have a like a stretching, right, or compression factor, whatever you call it, right? That number B, right? We've been playing it in the past, and T is the independent variable. Now, if you don't like this kind of a real world notation, so you can rewrite this function as a dependent variable y it is given by a function f of x, where x is the independent variable, which replaces the t. So that follows 12 times cosine of pi over 4 times x, okay? So now, without telling you too much, take a guess what letter A is asking for. The maximum displacement. X. Amplitude, right? So now you see that I sometimes didn't have to explain to you. It's just by understanding what I mean by displacement, right? So I think that as far as I understand the word displace, so I move something from one place and put it somewhere else, right? That's the movement. But if you make it as a noun, that's how much you're moving something. And therefore, that D measures the distance or the amount of displacement that the marble is away from that reference position. It's just a distance, right? But I like Max put it in a term that we have learned, right? So the maximum displacement is just nothing but amplitude. Amplitude. How much is it? Yes, amplitude is 12, right? And what units you use for amplitude? You usually don't have to worry about it, but now it's a real world situation. The amplitude does have a meaning, right? It's measured in centimeters, right? So it's 12 centimeters. Okay. Let's skip the letter B for now, right? Let's think about letter C. What do you mean by really long? No, it's a term, right? Frequency. I have to tell you know what it is. But in letter C, is asking for the time required for a cycle. Now, do you happen to know a terminology from the discussion of sine and cosine function back then that seemed to represent the same thing, like a time for a cycle? Period, right? So yes, it is period. So that's why I want to just think about letter C first. So yes, time required for a cycle is nothing but a period. So now, how much is the period for this function? Now, let's say in general, a cosine function has a period of, cosine and sine function has a period of 2 pi radians, right? 2 pi. What's up? But is it going to be 2 pi if you have a rescaling factor? You know, it's being stretched, compressed, right? So I think that the formula is 2 pi divided by, right, whatever constant they put it there. We used to call it b, right? So now it's just pi over 4. Right, so we do keep change flip. So 2 pi times 4 over pi. Pi's cancel. All right, so you're left with 8. Now again, in what unit? Seconds. Good. So you realize that it's the time measurement, right? Seconds. Okay. Now, so like I said, you know, you've got this already, right? Based on our previous discussion of sine and cosine in general. So now you just have to build a connection between the terminology in physics, right, and the things we have. And therefore, you're usually expecting some similar or even consistent terminology, right? And the reason why you call it amplitude is later on, you know, we actually end up using amplitude a lot. Now, letter B. What is the frequency? So let me give you some real world examples so you can understand the relation between frequency and period. So how often a leap year is going to occur? Every 4 years, right? But when you say that every 4 years, it'll be a leap year. It's not talking about how long it takes for a leap year to occur, even though it's pretty much saying that it's going to take 4 years. But you're telling people it's so long, right? You know, you're going to have to wait for 4 years, right? If you're not that lucky that you're born on the 28th, wait, 29th, right? February 29th, you have to wait for 4 years, right, to have a birthday. It's just kind of cool because, you know, you can see that on the age, right? 1 year every 4 years, right? But I mean, you're just tricking yourself.
Like if like one girl, she was born February 29th, then she did like her first birthday like on the leap year. Does that mean she will be 2 years old?
Yeah, for example, you guys are probably like 16 years old, right? Something like that. If you're born on February 29th, right, you could be 4 years old. You only have 4 birthdays, right? Anyway, so like you're living life, you know, a time traveler, right? When people are like 4 times older than you, you're only 4 years old, right? But you're so premature because you know you already know a lot of things as a 4-year-old, right? You can brag about, hey, I'm only a 4-year-old, right? Anyway, now we were thinking about once every 4 years. That's talking about frequency. But let's make it even more like a frequency, because frequency is like how often something happens, right? So the frequency for the leap year is once every 4 years. But let's write it as 1/4 per year. How do you understand 1/4? Or let's say 0.25 per year. What does it mean? So are we expecting a leap year every year? No, we're expecting a leap year every 4 years, but that means on average, we're expecting a fourth of a leap year every year. Can I have to wait until the end of the 4 years to get a whole leap year, right? Now that's why, every year you think that's 365 days. Not quite, because on average you're getting what? 265.25 days, right? So every year you're getting a quarter day. So you accumulate them for 4 times, you get a whole day, right? That's leap year, right? So now frequency is however many times something occur or reoccur per unit time. Unit time means that it doesn't have to be always a year. It could be a year, a second, a month, a minute, right? Now, simply put, period is the reciprocal of the frequency. Frequency is the reciprocal of the period. It's that simple. Okay? So now, can you guys imagine? Hey, the frequency of the leap year is a quarter per year, a fourth per year. What is the period for the leap year to occur? It'll be 1 over that, which, as you know, will be 4 years, right? So now another example. At lunchtime today, we had a brief celebration for Dr. Barron's birthday. Dr. Barron, yeah. I don't know if it's today or it's exactly today. Okay. Yeah. So then a lot of instructors brought the food, and there's some chicken wings from Publix, and I ate a few of them. How many? 4. Say. Let's go with 4.
Let's go with 4. That's
So now I'm trying to use it as an example. So if it's better to write it down. All right. So now 4 wings, and it took me. Well, guess how long it take me? It took me to finish 4 wings. 2 minutes. Is it fast or slow? Fast? It's small wings, right? Anyway, so now let's compute the frequency of me eating the chicken wings. Frequency. How would you calculate it to let people know how fast I'm eating chicken wings? Or was it the other way around? All right, let's try one way or the other, right? If you say it's 4 wins over 2 minutes, and you simplify, you get what? 2 wins per minute. Is that frequency? Every minute, me eating the chicken wing is gonna appear twice, right? So I finish the win, then I do it again, right? I did it twice in a minute. So that's frequency, right? So now, how would you get the period? Yeah, flip it. Now, does it make sense though? If you're thinking about the period, that means how long will it take for me to get to the second win? Right? I finish the first one and I wait for how long? Well, you go with 2 minutes. Oops. For win. So that's 0.5, right? Minute for each wind. Right, so now it's a time, right? It's how long it takes to finish a wind on average. So that's a period, right? Again, just like the leap year, it takes 4 years, right, to appear once. So every leap year, it takes 4 years, right? But the other way around, there will be only a fourth of a leap year every year, right? So now you see that why the period and frequency are reciprocal of each other, right? Now, for me, even though I do teach physics, but I do find the period somehow more intuitive to me. If someone tell me the period for something, I know that, oh, the longer the period, the longer the time, the slower it is, right? If I tell you that it takes me an hour to finish, some noodle, right? It will be super slow, right? But sometimes people like frequency a lot. All right, so now let's get back to that problem here. So how do we compute a frequency? It's as simple as getting the period first and do the reciprocal 1/8. Right? Now the units, be careful with that. It's not going to be seconds anymore. It will be per second, right? If you like decimals, it will be 0.125, right, per second. Or you know what? It could be sometimes written in a fancy unit, which is called hertz. Right? You guys heard of hertz before? Right? Yeah, that's the standard units in physics for any kind of frequency. So some interesting facts about the frequency of our life. And it turns out that we can hear a wide range of frequency of the sound. Sound is the vibration, right? So let's say you speak, right? Your vocal cords gonna vibrate, right? And you know that I think that say your mom tend to have like higher pitch than your dad, right? So that's why you can tell right away that's mom yelling you, not your dad. So you can go by the frequency. Now, as human beings, we are able to hear from as low as 20 hertz of a sound up to 20,000 hertz. A hertz means how many vibration, right? Go up and down, right? Happens in a second. But 20 hertz means that you're gonna go up and down for 20 times in a second. So can you imagine 20,000 hertz? That'll be a lot faster, right? But as we get older, our ears, is getting less sensitive. You know how ear works, right? They have a membrane here that's gonna vibrate, right? It's gonna send a signal to your brain. You're gonna interpret it as a sound. But when it's getting older, it gets a little bit stiffer. It doesn't vibrate as much as when young people does that. Therefore, the dog whistle, right? If you blow the dog whistle, it produces a sound that sometimes you can barely hear it. It's not because it's low or not as loud. It's just in a low frequency. And it turns out that maybe senior citizens, they're not gonna hear the dog whistle because it's just too low for them to hear it. But now at your house, you have Wi-Fi, right? And now everyone has this kind of Wi-Fi with 2 different frequencies. They have like a 5 GHz, right, and a 2.5 GHz. And it turns out that the higher the frequency, just like the higher the pitch, right, the easier you can get the sound to penetrate. And that's why when your mom yell at you, you can hear it right away. When your dad says, "Hey, go get your work done," you can barely hear it. Right? It's interesting. It works out in a very similar way. But sometimes, if you do want to have a better coverage, so let's say if you do have a lot of doors and rooms in your house, right, then the signal might not be as strong as you thought with the 5 GHz, because they do get pretty fast speed and it carry more data, but it penetrates the wall, not as good as the 2.5 hertz. Anyway, 2.5 GHz. So now let's take a look at a question at the test level to see if you guys can already figure it out. All right, so for this kind of question, like 64, it's definitely going to be multiple choices because there's not much you have to show me except for you to just understand the concept. All right, go ahead and give it a try for 64. I'll give you 1 minute. because it's as straightforward as it is. You know, if you know what those terms are, you should be able to figure it out. All right, 64, go ahead. All right, have you guys decided what to pick? Pretty much, right? Let's do that as a whole class, right? Raise a hand to let me know if you're gonna pick A, B, C, or D. All right, some pick one, letter A, and letter D. All right, well, it's either A or D actually, right? And the answer is letter D. And the reason why is that's, again, I don't blame you because remember Max just mentioned, so displacement is what? The same thing as amplitude. The amplitude is just a number, right? It's a positive number. So whether or not you see a -4, it will still be 4. It's just to be 4 meters above, right? 4 meters below the middle line, right? Well, I guess that you can tell from the period that just go by 2 pi for the period for sine, divide by 3, right? You get, what the period is, and the frequency will be the reciprocal of it, right? But just be careful with, the sign. But when we get into the physics, your teacher will definitely going to tell you that displacement could be negative. It's a vector. So now what's going on is obviously, whoever made this problem is not going to be expert in physics. They feel like that, just want to call it, the way they want. It's not very rigorous. So that's why I'm not going to be too crazy about explaining to you why displacement has to be a vector. But just make sure that when it comes to displacement for a simple harmonic motion for our test, it's as simple as amplitude, right? And you're never going to go negative for the amplitude, okay? Now, one more, and you're good to go. All right, 66. Almost the last question on that updated packet for test number 2 review. All right, give it a try. So you're going to go backwards, right? Given those information, you can identify which equation or function that describes this simple harmonic motion. Want to go? Be careful, they say it's the frequency, right? 8 vibrations per second. All right, so yeah, it's almost the time. Let me tell you that it's the letter B. All right, so the way it works out is, now again, I'm a big fan of a period. So when I see the frequency, I'll invert it to get period, which is 1 over the frequency, right? So that must be 1/8 But I know that the way we calculate the period is take 2 pi, right, divided by whatever constant is in front of the t, and somehow they use that fancy letter omega, right? So now you're solving for omega, right? And I'm sure that you do the cross multiplication, you'll see that omega has to be 16 pi. Now, if you're wondering what that omega stands for, it's the same omega you saw back in phi 1 or phi 2. We used to call it angular speed, but now it's called angular frequency. But there's no need for you to know that since they didn't even mention it in the textbook. It's just the number in front of the t, and you need to use that to get yourself the correct period or frequency. That's all. All right. You're good to go, and please don't forget that homework 5.5 to 5.8 will be due tomorrow at midnight. Don't miss it.